Continuous random variables. So these are the variables that can take any value within a given interval. In other words, they can take infinitely many values. Okay, basically they are real numbers in an interval. So let's take a look at an example to understand what it means. Let's say you test a single light bulb and you record how long would it last before burning out. So this is your light bulb. So here, my each outcome corresponds to a specific lifetime. My bulb could last maybe 0 hour. Okay, it could last 1 hour, 2 hour, 3.1 hour, or 4.652 hours. It could last any number. So it can essentially take any positive real number. So my sample space in this case is from 0 to infinite. So this is my Venn diagram representing that sample space. So 0 hours means it burns out immediately. So here, my X represents the lifetime of the bulb that I bought from the store. So it can take any real value between this interval, 0 to infinite. So if this is my sample space right here, okay, let's say this is my sample space. So what's happening is I have this mapping. Okay, if let's say my bulb, right, say this is a 2 over there, right? This is 2. This 2 will get mapped to 2 over here. If this bulb lasts exactly 2 hours, so this 2 gets mapped to this 2. Well, what if it lasts 6 hours? Okay, right here is a 6 hours. So in this case, your 6 gets mapped to 6 over here. What if it's like 3.1 hours? So there is a 3.1 over here, 3.1. So 3.1 will get mapped to 3.1 over here. So in this case, think of this X as a mapping. Okay, it's basically mapping a number over here from your sample space to a number on your number line right here. By the way, in this particular instance, my X and my omega are exactly same. Let's say you're measuring the height of people in a crowd. Here, my sample space, omega, is a set of all possible outcomes. Basically, all possible heights that you can get when you select people from this experiment. So we know from experience, let's say this is given to us, that the height of any person is between 0.8 to 3 meter. We know that from my experience. In other words, your height can be 1.75 meter, 1.755 meter, it could be 1.32 meter, it could be any number between 0.8 to 3 meters. So my sample space in this case is 0.8 to 3. My sample space is one dimensional. So using my Venn diagram, if I represent my sample space like this is how, let's say, it looks like. Now you can map. So let's say you randomly select a person and you measure his height. Well, his height can take any value between 0.8 to 3. So let's say his value is 2, right? 2. So this 2 gets mapped to 2 over here. What if you select another person? His height is maybe 1.5. So this 1.5 gets mapped to this 1.5. In other words, every value that you can get over here, you can get in this space over here. So think of this X as a mapping function. So in this particular instance, my X and my sample space are exactly same. Suppose you're playing a game of tossing a dart at a circular board of radius 1 meter. This one right here. This is your circular board of radius 1 meter. So each place where your dart lands, you record where exactly it lands. So in this case, each outcome is a point on this board. So this is an outcome right here. Let's say my dart lands over here. So this is my outcome right here. This is another outcome. Let's say my dart lands over here. This is another outcome. Or maybe it lands over here. So these are my outcomes over here. So I can represent my outcome using this expression. This is my sample space. And what this is saying is that x squared, like x and y, such they belong to R2. Okay, they basically are belong to a two-dimensional subspace of real numbers, such that your x squared plus y squared is less than or equal to 1. What this line is saying, what this condition is saying, is that your x and y are always going to be lying within a circle of radius 1 meter, or they could be lying on the circle, but they're never going to be lying outside the circle. They're always going to be lying in this area right here. Okay, the point's never going to lie outside the area. Okay, now let x be the distance from the center of the board to the point on which the dart lands. So let's say your dart lands over here, right here. So in this case, your x would be this distance right here. Distance from here to here, that would be your x. By the way, this is capital X and this is small x, small y. Okay, so this is my distance right here. Okay, now if you think about it, your x can go anywhere between 0 to 1 because your dart can land over here, right? It can land over here. In that case, your x is 0, or your dart can land over here. In that case, your x is 1. So your x can go from 0 to 1. So your x from 0 to 1 right here. This is all your x can take. Okay, so let's understand this through an example. So let's say this is the point. Okay, my dart lands over here. So what is my x in this case? Well, the dart lands over here. Using your Pythagorean theorem, calculates this distance, and this distance is given by this expression right here. Okay, and this comes out to be 0.707. So this point right here, this particular point, the number associated with that is this distance, 0.707. So map this point to 0.707 over here. Same thing. Now you do the same thing with the other one. Let's take a look at this one right here. This point is 0.8, 0.5. So this distance from here to here is going to be, use the Pythagorean theorem to find this distance, and the answer comes out to be 0.94. So this distance is 0.94. So this point gets mapped to 0.94 right here. Okay, so this way you can map every single point in there to a corresponding point on the real number r, and these points will always get mapped between 0 and 1. So in this case, your x, think of your x as a mapping function that's mapping your set of all, your sample space to a number between 0 and 1. Now let's take a look at an example from physics. Let's say you have a ball on a slope, and the angle of the slope is theta, and you give some initial velocity from here. Okay, this initial velocity is v0. So you record how much time it took to reach at the bottom, from top to the bottom right here. Now this time, it depends on many physical factors. It depends, for example, the initial velocity, right? If you give a high initial velocity, it's going to come down at the bottom a lot faster, a lot earlier. Also depends on the angle. If your angle is low, it's going to take a long time to come here. But if your angle is high, it's going to come down very fast over here. So let's say your initial velocity goes from 0 to 10 meters per second. Let's say this is given to you. Also given to you that your angle, okay, this angle right here, it can go from 45 to 90 degrees. So each trial, in other words, each roll that you perform has a different combination of these parameters of your V0 and your theta. So the sample space in this case would be represented as this expression right here, V0 comma theta, where your V0 is going to be between 0 to 10, right? That's given to you from here. And also your theta can be between 45 to 90 degree. Again, that's because it's given to you. These are the constraint that's provided to you. So in this case, my sample is a two-dimensional because there are two, right? There are two variables. Let x be the time in seconds it takes for the ball to reach at the bottom. So let's say you put some v0 and this angle theta, and the time it takes to reach at the bottom, let's say, is denoted by x. So the formula for that, using principles from physics, is given by this expression right here. So this expression tells you, it relates your time it took to come at the bottom with v0 and theta. Okay, now when your initial velocity is 10, okay, and your theta equal to 90 degree. So initial velocity is 10, theta equal to 90 degree. Basically what it means, sorry, let me just come down over here. So this angle right here, theta, this becomes 90 degrees. So in other words, this is a steep right here. It goes like this. So your ball is over here and you just go straight down. So your initial velocity is given to you. Okay, initial velocity, whatever is in this case 10, and theta equal to 90 degree. So it's saying that your x is going to be 0.095 seconds. Okay, they calculate this thing using this formula. I substitute the value of v0, substitute the value of g, which is acceleration due to gravity, and I substitute my theta in there, and my x comes out to be 0.095 seconds. And so in this particular case, by the way, the ball takes the least time. That means your x is minimum. It reaches the bottom very fast. On the other hand, I took another case when your v0 equal to 0, meaning your ball is, this is like this, your slope is something like this, okay? And this is 45 degree, my angle is 45 degree. So this is 45 degree, and I just let the ball go on its own. I am not giving any velocity. So this time when the ball reaches at the bottom, it took around 0.53 seconds. How do I know? again from the formula right here. I'm just substituting v0, I'm substituting g, I'm substituting sine theta, and it gives me the answer right here. Okay, so it took me 0.53 seconds. So in other words, my x in this case is going to go from 0.095 all the way up to 0.53. So this is the range of my x. So this right here, I'm representing my x right here. Okay, this is where my x can take the values. Now, my sample space, on the other hand, that depends on these ones right here, V0 and theta. And my V0 can go from 0 to 10, and theta can go from 45 to 90 degree. So I put these conditions on this plot right here. Okay, this is my V0 right here, and this is my theta right here. So I put my V0 between 0 to 10, right? And my theta goes from 45 to 90 degree. So this is my sample space right here. So my x, okay, x which is the time it took, it maps all the numbers from this sample space to a number on this number line right here. And these numbers are always going to be between 0.095 to 0.53. So this is kind of like a mapping function right now. Now I'll give you the formal definition of random variable. That should make sense now. So it's a random variable, it's a function, and what it does, it assigns a numerical value to each possible outcome of your random experiment. So this is my set of all possible outcomes over here. And what it does, this random variable, it's basically taking an element over here and assigning a number to it. Okay, and that number is going to be falling between minus infinity to plus infinity. It can take any value. Hopefully, now this makes sense to you, and I hope you are a happy person now.